Hello, this is going to be Chill Maths, coming to you on a Sunday afternoon, just broadcasting mathematics onto Twitch. See what happens. Hello, that's Joma! First time in chat, and with the cutest emoji that I've never seen before. What is this? Is this from somebody else's? It's just Dino Dance. It's a global emote that I've never seen before. Thank you for bringing that into my life. Hello, Neutrino. This is going to be a kind of math stream. There's Mary as well. Hey, nice to have people here. Oh my goodness, look at this. Little maths community just hanging out on Twitch, just in between all of the other like Fortnite streamers and people doing their own stuff. Just got a quiet little maths corner. Although I'm going to ruin it by doing an unrelated story time, but not really. I just want to tell you about this band I've been listening to. There's this band I've been listening to. They've done the funniest thing, and I just want to tell people about that if you like. But if you don't want that, then there's Chill Maths on the screen as well. Look, here's a proof by induction. So story for this one is on Friday. Let's show me you actually put maths into Twitch or something. Hey, nice to meet you. Sometimes people do that and are surprised that, hey, look, we're doing the thing. Here's some proof by induction. We showed this to some incoming students. Thanks for the follow. We showed this to some incoming students as an example of proof by induction. What does that look like? And one of them asked me a really good question, which is something to do with something we say about how many base cases there are. So there's this sentence here, which might or might not be true. And I've been thinking about it, and I'd like to talk about it, because I think maybe this is not correct. I think maybe you only need one base case. That was their question. I mean, their question was, why do you need two base cases? And then after a bit, it was, when do you need two base cases? And actually, I think the answer might be you don't, maybe. Story time there about band that I like. So I listened to this band. They're pirate themed. It's one of those sort of slightly heavy metal bands. They do metal, but they're pirate themed. It's not quite a parody band, but it's not a very serious band. They're called Visions of Atlantis, if you want to look them up. They do pirate metal, sort of, which they've really leaned into recently. They've been going for ages, like 20 years. It's one of those bands where they've got like 20 different people in. Let me show you the chart on Wikipedia. There's a good chart for this. And one of those bands that's been running for absolutely ages and has had just like 20 different people in it. Here's their chart. I love it when bands have a chart like this. Am I broadcasting that? There we go. There's different people in the timelines. If you're the person behind the scenes who makes these charts for Wikipedia, I love these on Wikipedia. Hello, Threshy as well in chat. I'm telling a story about a band I like. There's only one core member of the band at the bottom here, who's the drummer. He's just been keeping it steady the whole time through the 20-year history of different people. Actually, there's about 20 people who've been in this band. Yeah, hello, that's me. This is where I talk about pirate metal instead. They recently leaned into this because previously their albums have been named vague things like Eternal Endless Infinity or Castaway. That's quite piratey, I suppose. But recently they leaned into it and they actually made an album called Pirates, which, at some point you've got to lean into it, right? We're the pirate band. We're going to do a pirate album called Pirates. But the best thing they've done is that they've released a kind of sequel album. The sequel to Pirates is sort of called Pirates 2, but because of the Roman numerals, you can also pronounce it Pirates. Aye aye, Armada, which I really like. I think it's the best thing they've done. Lean into the pirate elements of things, do a load of pirate-themed songs, which I guess they've always kind of been doing, but name your album Pirates. Aye aye. The only thing they need to do next is release an album called Pirates. Aye aye, Captain, and that'll be even better. I guess we can hope for the third one. Anyway, that's a band I like. There's not. If you're looking for a parody band, so if you're looking for that kind of idea, but like a parody band, I guess you could listen to Ailstorm as well, or you could not listen to Ailstorm. I mean, you've got other stuff that other stuff you can do. Right, okay. I'm still really taken by the idea that Lasjoma has typed maths into Twitch, has found me, and then also aware of Oxford live streams. And I'm sort of sorry that it's me again. There are some other people. Oh, do you got any recommendations, Neutrino? Yeah, drop your recommendations in chat. That's right. This is now Chill Metal Stream. The one time somebody joins looking for maths, we're going to switch it all up. Just talk about silly metal bands and their silly metal ways. I thought it's not even quite right. I know if you try and discuss genres or labels, then it's just a whole can of worms. But I'm not even sure. No, it is. It's kind of that melodic, almost operatic sort of stuff that people do. Yeah. Let's not do genres. Right. Okay. Says right. That's the metal that I'm into right now. Metal-ish. Metal's a big tent. Let's talk Fibonacci numbers. Because I think this sentence that we've put for the incoming students is wrong and maybe a bit misleading. Because it is true that the Fibonacci numbers are defined in this way, where you have each one is defined in terms of the previous two. But I'm not sure we actually use that fact anywhere. After all, what we've got is really a series of statements. So I tried to skim this when they asked me to remember how this works. So there's two basis cases over here where we've used the facts that we know what F0, F1, F2 and F3 are. Oh, that reminds me there's F1 today. I need to go. I might cut the stream short and go do F1 at 3 o'clock. It's the British Grand Prix and there's like 3 British drivers at the front. Will it last? Who can say? Okay. So there's an induction step down here. Yeah. Hello, Lazy Shooter 101. First time in chat. Induction. As many base cases as you have induction steps. It's sort of, what counts as an induction step in a way? How many of the previous statements are you using? And I know there's kind of people talk about weak induction and strong induction, where in one of those, and I can never remember which way around they are, in one of those you assume it's true for the previous integer, and in one of them you assume it's true for all previous integers. I think that second one is called strong induction but feels weaker because you're assuming more things. Yeah, it's called strong induction, isn't it? Cool. Yeah. Hey, maths 22222. Hang on, let me get that right. Maths 2222222. Welcome to chat, first time chat. Define this as a new function, then it's easier to see when you need one base case. Yeah, because I think that's what's happening, right? I mean, you need to use the fact. First line after, then you use the fact. Oh, hello. Oh, so right here, we're using the fact about how Fibonacci numbers work. Yeah, okay, so that's not true. That's not true. Okay. So we can't do that for the first couple of statements. If you had, do they agree with all the numbers going on here? Are we out by 1 maybe? Because I still think you could do that for F2, couldn't you? You could do F2 F0 minus F1 squared. You could rewrite that as F1 plus F0 minus F1 squared. I discovered a kind of new problem. Are we going to use the next one? You could do that. But then at some point you're going to need to know what these numbers are or something. Messy. Right, okay, so we are using this fact. So maybe we do need two base cases, because it doesn't help me too much that this is like, so this is like the n equals. Really struggling with what the value of n is. Is this even the statement for n plus 1? I guess it is. And that's the statement for n is 2 with an f1 in here. So then if I read here, when n is 0, this is nonsense. When n is 1, this is f2, f0. When n is 2, this tells you something. Lazy Tutor thinks in the bit after then the minimum index gets down to n minus 1. So this would be the case for, okay, so that's the inequality Lazy Tutor's given me, is this thing up here. Maths 222 has made the audacious claim, I think, that this fact is just clear without using any base cases. I'm not sure if you mean the overall fact at the top, which is kind of well known about Fibonacci numbers, I suppose, or whether you mean the recurrence that we're using. Okay, so maybe we do need to, because we are inherently using a thing about Fibonacci numbers. Our plan here is to take the highest index we can see, which might be f3. Oh, Maths 222 is only using one base case. Yeah, so the question I suppose is, can you prove this n equals 2 fact? In the same way that we're proving stuff down here. Like, can you expand f3? Yes, you can, in terms of f2 and f1. And then that should just relate this back to the previous statement, which we have, right? We're only using one previous statement. Let's try writing that out. I regret this bit. And I regret this bit. Well, no, I don't. That was a good observation. Thank you, chat. Chat's helping a lot here. This is good. We have a strong. I think someone called it backseat chat or something. I was trying to do something in Minecraft, and chat was very helpful. I think there's a phrase for that, where chat does all the work. Right. Okay. So my question is, can I prove this using this proof strategy, just assuming the previous line is true? And I think it's all right. Hey, it was Mary. Okay. Okay, so I think if I just copy this all out with n equals, irritatingly, I'm going to copy it out with n equals 1, right? Compared to this stuff. Oh, well, never mind. Let's not overthink it. So this is still true. f2 plus f1 times f1 minus f2 squared. And then that would be, I can rearrange this. I'm still plugging in. This is still true. Oh goodness, is this true? I've got confused. f2, f1 minus an f2 squared. Bring together the f2 squareds, and there's an f1 squared. That's just true by rearranging stuff. And then this line. Ah, we're using Fibonacci again in here. Using Fibonacci again in here. That's fine, because I have f1 minus f2, which is still minus f0, which is that's a thing. I think I'm all right. So this is negative f2 f0 minus f1 squared, which is the previous thing up here. So once you've done this base case, I think you can relate this one, this next one, using this argument. I think you can relate it to the previous one. I think you agree you only need one base case. I mean, you definitely need at least one, don't you? This is not well formed for n equals 0. For n equals 1, it says something sensible about Fibonacci numbers. Which, how are we counting these? 0, 1, 1. I still sort of think you could prove this with. Is this toxic that I still sort of believe I could subtract 1? Oh no, I can't. Okay. I can't prove this first thing using the inductive logic, because there's this f0 down here, which I think if I pushed it a bit more would be an f minus 1, which is not okay. Yeah, And the other suggestion is you use Binet's formula, which is just there's a formula for Fibonacci numbers, and we discussed this a little bit with I discussed this a little bit with the students as well. You can do this without induction if you separately believe the formula for Fibonacci numbers, which is something 5 to the n plus something else to the n divided by root 5. If you separately believe that for reasons that don't involve induction, then you can, well, you've kind of moved your induction question into the why does the formula work? My favourite way to prove this, and this is just a variation on the algebra down here. I think the algebra is a little bit confusing about what we're doing. My favourite way to do this is to recognise this as the determinant of a matrix. This matrix, to be precise. The determinant of this 2 by 2 matrix is fn plus 1, fn minus 1, take away the square of fn squared. And that's all very nice. All I need to prove is that this matrix is related to this matrix, the kind of previous statement for my inductive, I guess my inductive step, or something like that, is to show that this matrix is related to the previous one. And it is. I have to put exactly the right numbers here, which I guess is a little bit of magic, but I can do that. Give me a second to make the magic work. This is going to be very cute. I'm going to put a matrix here to explain how to get from these Fibonacci numbers to those Fibonacci numbers, and the determinant of the matrix is going to be -1, so that when you do the determinant of this huge product of what you're really doing to generate the matrix is multiplied by the same transformation matrix again and again and again, which is why there's a -1 to the n from doing it again and again and again. The determinant of that huge product is fine. All I need to do is get this right with no messing up. And if you've seen the stream before, that is a tall order. What's down here? So this row down here, the output down here is just you take the top row. How do I take the top row? That's not hard, is it? I do 1, 0. And that's sneaky because now for this bottom row, it's going to read off the top row. How do I get fn plus 1? Well, you add the things together. I think this works. I'm trying to do I've only got one pointer, but I'm trying to do the matrix thing, right? Hang on, I can draw stuff. Powers of drawing. I'm trying to make it add. fn minus 1 gives me fn plus 1. Fn minus 1, fn minus 2 gives me fn. Good. Nice. This thing just gives me fn. This thing just gives me fn minus 1. Good. Drawing. Yeah, okay, cute. To quote chat. So then, well, each time you want new Fibonacci numbers for your determinant, which you're creating, you're just doing a huge stack of these, n of them, until you get down to, so if I do a kind of dot, 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 this has been applied n times, whoosh, to the kind of original thing. Oh goodness, I'm going to be out by n minus 2s, right? I shouldn't go too far, because I should stop before I get to, I don't want to make this negative, so that people don't get upset. So let's do n minus 2 of them. And if I take off n minus 2 of them, maybe that wasn't very ambitious. I get f3, f2, ooh, f1, f2, f2. Maybe I could have been more ambitious there. Anyway, this thing has got some particular numbers in it, right? Yeah, I'm doing something like this calculation down here. 2 times 1 take away 1 squared. Yeah, something like that. I could maybe push this one more step, right? F0 is defined, I think, in this world. So I should maybe have pushed one more step. I'm going to push one more step. I'm trying to work out what will happen, and this is induction, I suppose. Work out what will happen if I do multiple steps back to get back to kind of base case, where I can use the values of some Fibonacci numbers. Yeah, one more step would be n minus 1, wouldn't it? Thank you. Those darn negative numbers. And if I'm doing that, then I need to change everything. I'm not sure I love this, because then I'm going to get an extra minus sign. I'm not sure this is very elegant. This is then 1, 0, 1, 1. Oh, so it is just 1, 1, 1, 0 to the n. I guess I knew that deep down. I guess if you can't remember Binet's formula for where the Fibonacci numbers come from, one option that you have is to diagonalize this matrix, and then once you've diagonalized it, the power of n just gives you the eigenvalues in the diagonal matrix in the middle, being raised to the power of n, and you've got P and P inverse out there. Ooh, what's this? It's a step paper from last year with a request for a particular question. Chat Phil. Put it on screen. Oh my goodness. They took my favourite thing and they made it into a step question. Yeah, proof by induction. Oh no, okay, proof by induction. No, my claim that this is not really induction has been undermined by this step question telling you to do it with induction. Oh yeah, we did it. Have we got any marks? Wait, this just instruction is just sort of floating outside of any part of the question. This is a real step paper. Looks real. Why is this instruction just around? Oh well, never mind. Yeah, then do its determinant. Oh, that looks fun. But essentially fine, right? Use the m plus n. Where, oh, careful, because m and n appear to be vectors. I should stop throwing shade on this step paper. That's not. Part 0 is normal for step. Okay, interesting. Cool technology. This is fun. Ooh, oh, this is really good. Oh, I still want to do this question, but maybe not on the stream, because we did some step questions on the stream before, and it was, oh, it's a lot of work. It was not very chill. So we stopped doing that. But not because Cambridge told me to, which is what I jokingly said would happen. This looks good. Part of me does miss how much, like, you can just go so far with these. This is step 2 as well. There's so much question here. Right, cool. I'm getting distracted by that. Good. I wonder if you can do the whole step question just using Binet formula stuff. Diagonalize the matrix. Oh, there's the golden ratio and the silver ratio, or whatever the other one's called. Oh, bro, now I've got my formula. You want me to prove a load of stuff? A whole bunch of geometric series. Baby. You're going to put powers of 2 in there? That's alright. Still a geometric series. Or some sort of big binomial. Yeah, this will be fine. This is so good. This is quality question writing. Anyway, right, okay, I'm getting distracted. Let's leave that for now. Switch. Here's another thing that someone showed me on that meeting. I had a meeting with some students. I'm now farming that for content, kind of trying to work out what I should have said. Because what I actually said was, oh yeah, I reckon that only needs one base case. And I think, hang on, I'm wrapping up. So right, what's our opinion overall? Hang on, sorry, where do we leave this? I think I can do this with only one base case. Because I think it's secretly just a big power of this matrix applied to an initial matrix. Yeah. Yeah. One base case. I agree with maths. 2, 2, 2, 2, 2, 2, 2. Right, okay. A different student showed me a TikTok where somebody I haven't met before called Math Scribbles on TikTok was demonstrating a sort of integration technique that I think from context clues, I think they invented. So I wanted to show that off. Look, I put that in if you want to follow them on TikTok. I'm not on TikTok at the moment, so I couldn't. They can do the class of integrals where you're integrating from minus a to a with e of x. E of x is supposed to be an even function. And downstairs k of x plus 1, where k of x has the weird property that k of x times k of minus x is 1. Their example of this is something like, if you're doing the integral from I've forgotten what they put upstairs, but whatever, -1 to 1 of like 1 plus x squared over 2 to the x plus 1, because you see that's even, and 2 to the x times 2 to the minus x is 1. You don't worry about the plus 1, that's just there. Their strategy for doing this integral is kind of nice. It works like this. To do the sub, u is minus x, and then there's a minus sign from the sub that flips the limits and they come back again. It's got symmetric limits or whatever, and this thing's even, so whatever. And this is k of minus u, but we know a fact about that. Then use the fact that this is 1 over k of u. So if I call this integral I or something, here's the integral after the substitution. Flip this upstairs. By multiplying top and bottom by k of u, which, because of this weird cancellation fact that you've got, k of x and k of minus x have to be equal to 1. Now you've got your original integral and this new version of your integral. Add them together. Do what I thought it would. Yes, there we go. Add them together, and you get 2i on the left is equal to the integral from minus a to a. Upstairs, I'm going to change the variable from this u thing back to x again. And they've got the same denominator of k of x plus 1. And this one's got nothing upstairs, so it's got 1 upstairs, and this has got k of u, which I'm relabeling to k of x. I guess maybe I could relabel both of them to t or something else so that the variable matches. Anyway, that cancels. K of x plus 1 upstairs is the same as the k of x minus 1 downstairs. So you're left with just having to integrate your even function, which I suppose that's another condition, that if you see this integral, you need the limits to be symmetric, you need e of x to be even, you need k of x to have that property, and you need a guess, and you're willing to integrate e of x. If you can do that, then you can do this integral, because it kind of just turns out to be 1/2 of the integral of e. So I saw this, I watched the TikTok, I thought pretty much the same as Thrice Shy. Huh, that's nice. What's going on here? And that's a difficult question, right? What's going on here? Is this doesn't feel very general, but maybe it is general. Maybe it could be general. I'm never going to remember all of this sort of k of x, k of minus x. So is there something else that I can do? So something I was thinking about was maybe rewriting this stuff that they've done. The kind of key property of this cancellation over here. The key property of the cancellation has been disguised a little bit with this condition, and including the plus 1. Any appropriate functions for k other than exponentials? It's a good question. Could we get some more examples? That is a good question. It's a very good question. Yeah, hang on a moment. Well, I mean, I can think of quite a lot, because for positive x, define k to be whatever you like, and then for negative x, face the consequences, and it's 1 over that. But I think that's kind of not what you mean. Probably you're imagining k of x to be continuous or nice or something. Yeah, piecewise functions. All functions are piecewise if you express them as in pieces. You probably want f of 0 to be 1. You probably do want f of 0 to be 1. That seems like important when x is 0. But then I think you can kind of do whatever. You can even make it kind of nicely infinitely differentiable or whatever you want at the origin. So I can't even say up to some sort of continuity thing. Now you can do loads of stuff. Why can't I think of anything that you can do? Is the harder question. It's not true for any polynomials, is it? Because k of minus x would be a polynomial of equal degree, and then I'd be suspicious about these. Yeah, I can make it infinitely differentiable at the origin, but not equal to an exponential. There's a kind of standard trick for this. Oh, that's good. Does that work? That looks really good. Not nice when x is 1, but yeah, and interesting when x is minus 1, right? That looks pretty good. So if your limits are closer to the origin. Rational function from maths 2. There's this standard-ish trick for finding examples where, I don't know, well, the function I'm thinking of, let's keep it to that. The function I'm thinking of is this, which I've seen before as it's non-zero. It's not the zero function, but all of its derivatives at 0 are 0. Do I mean that? Quick Desmos check. Sanity check, really. Yeah, this one. I do mean this. It's not the zero function, but it's extremely flat at the origin. You can prove that all of its derivatives are 0. So I guess what I want is not quite this, but then something using this, like add this on one side, and that will affect. So if you have your perfect exponential function, I will add on the right hand side, I'll add this, and that'll still have lots of nice smoothness at 0, and then on the other side I'll just change the values, and I reckon that will work. Yeah, if you try differentiating it, you keep getting 0 at the front. I think we're using the fact that exponentials beat polynomials quite a lot. It's the sort of exercise that you do exactly once in your life to check that the derivatives of this are all 0 at the origin. And once you've done that calculation once, you get to use it as a counterexample lots of times. Because, well, now you know that there is a function where all of its derivatives are 0. It's kind of an interesting example for things where you're trying to analyze whether something's a local maximum or local minimum. So the thing that people draw is kind of this thing. Where so there's a local maximum at the origin. That's a local maximum here, but you can't prove that by considering derivatives at the origin because it's extraordinarily flat near the origin. A friend of mine suggested that you could use this to annoy someone by building a table where placing a ball on the table, it will, if you miss the origin even slightly, it will roll off the table, but they can't prove that using derivatives. Maths has moved that singularity to somewhere else. Let's have a look at that. I'm going to add a slider. Thank you, Desmos. I would love to add a slider. So I guess the argument here is that I should plot f of minus x, maybe 1 over f of minus x, to get the same graph. Not my greatest Desmos visualization, especially if you're red-green colorblind. Good, okay. We found some other functions that do this. Oh, not yet. No, not yet. I really do like that e to the minus 1 over x squared. I think it's an example. If you've got, so here we've got, think first, then speak. Here we've got an exponential, which does the thing that we wanted, and now an infinite family of rational functions. Thank you, maths. We could maybe modify these by adding some clever combinations of these exponentials. I'm not quite sure. I think I'm adding it for positive x and then adjusting the values for negative x afterwards so that this remains true. Anyway, I think I would prefer this if the +1 was somehow packaged into the function. When I first saw this, it took me a while to work out what was going on because, well, I kept looking at 2 to the x plus 1 and thinking, well, this just isn't true, right? If you put in minus x, you don't get 1. You get, well, there's some cross terms and you get another +1, but they don't mean with the +1. So I thought maybe I'd try and rewrite it into how kind of a slightly different way. This is going to be the same fact, but I don't know if we'll learn anything by doing this. I'm sort of trying to remove some of the whimsy. It's not quite whimsy, I suppose, but remove some of the 1 over 1 plus stuff. Maybe that's important because of the the family of solutions that was in chat a moment ago. But I guess we'll find out. What's the plan? So the plan is you can always do this. I'll still have e of u being an even function. So the plan is you can do this, and then I suppose what they really want is the plan is to add them to get 2i, and to use the fact that we've got e of these e's are the same. So what we'll get is something like f of x plus f of minus x. Again, I'm relabeling, which I know makes people feel uncomfortable, but I'm relabeling these u's to x's, even though I just did a substitution to say that x is not equal to u. There's a little bit of dissonance there. Maybe I should be using a third letter, like a t or something, to make people happier at the end. Anyway, this is good if, so maybe I would phrase it like this. We want this to be true, right? Or some constant would be fine. I'm more general now. Because then we'll pull the constant out and integrate the even function. Now, quick check, is this still true? Have I messed up? So if this is secretly this, then my fact becomes something like this. And this is true if, and then I think I have screwed up, haven't I? Sorry to hear that, neutrino. I think I have screwed up a little bit, or maybe not. So this is 1 over, if this is 1 over k of x, then things still work. This simplifies to 1. If f's derivative is even, then I believe f is an odd function. If f's derivative is even, I think f is an odd function, which then my original case up here would be odd times even, which I could probably show that's 0 anyway. Now I'm getting flashbacks to a time I messed up with minus signs and even and odd functions. Probably best not to. So okay, I was trying to work out. I think it's true that if this way round works, if this, then using the notation going on around here, f of x plus f of minus x equals 1. Yeah, I kind of don't really want this to be 0 because I have some other facts about when your integral magically turns out to be 0 if you do even odd arguments, and I know that trick already. I've got down to here where I've got my way of writing this using f, and their way of writing this uses the fact that k of x, k of minus x is 1. It's not obvious to me that the other way around works. This kind of, do you need to have k of x being 1 over k of minus x? I'm not sure you do. I'm going to do some multiplication up to find out. So this is going to be upstairs. Oh, plus 2 plus k of minus x. And on the right, oh no, I am wrong. It's nice to be wrong, proof by just multiplying the things out. Because if I just multiply up by the denominators, then I get, sorry for the handwriting, I'm not being very careful, everything cancels, and I get, yeah, okay, these things are equivalent. Okay, so we haven't lost any of the magic of the original, except maybe some minus signs. We haven't lost any of the magic of the original, but we have got some slight generality. So if I put a C in here for constants, then that would be a little bit hard to follow through here, because if I have C here for constants, then everything still works. It's just harder to express that as a fact about K. The fact about K looks even more wonky than it already does. No offense, but K of x, K of minus x equals 1 is a slightly strange fact. Because, yeah, this thing's going to have a C in front of it, and there'll be a bunch of these around, which I don't think would catch on as a... I don't think it would be taking TikTok by storm in quite the same way. This is 2 minus C or something. For any C. Okay, so I think the advantage of writing it with Fs is that we get the chance to write out a statement a bit more like this, where we can put this arbitrary constant C in, and it's not too ugly because it's just C on the right hand side. I can prove the F statement if F's derivative is even. If F's derivative is even. Right, you're going to differentiate both sides of this and tell me that, aha, F prime, and there'll be a minus sign here, F prime of minus x, which reminds me of all odd and even functions or something. Yeah, if it's even, then the derivative of this is 0 on both sides, so when you integrate back up again, you'll get 0. You'll get constants on both sides. I think if F's derivative is even, then I think F is an odd function. So there's a more direct approach, which is way back up here. If F's derivative is even, then F's an odd function. So I think in this substitution, you're just proving, well, the integrand overall is odd. So I think you get this kind of more direct approach where you say, aha, if F's derivative is even, then shortcut, this whole thing is just 0 anyway, because you've got odd function here. I think that's true. Oh, is it not quite true? Take not quite true. Doesn't mean F is odd, just F of minus x is C. Yeah, constant of integration. Yeah, I was being a bit lazy. Yeah, okay. Okay. F is almost an odd function up to a constant. Constant away, and then the constant will turn up, and that'll be the thing that I'm integrating. Okay, yeah, cool. Wait, is that all that's going on? Is that all that's going on here? At its heart, is this just inviting us to split an integral into an even part and an odd part? It really is, isn't it? Where we've carefully chosen ones such that the even part is the number 1. And you can write all functions in terms of their even part and their odd part. Okay, it's not going to set TikTok alight, but here we go. Yeah, that's just the odd part. That's just the even part of the function. Okay. If you have, I don't even need E in there, do I? I don't need E in there. Okay, let's try and do this in one take so that it makes a good clip for TikTok. Oh, TikTok videos are supposed to be that way around. If I turn so that I'm 90 degrees, there we go, okay. No, in portrait orientation for TikTok purposes. Hi TikTok, I've got an integration trick for you. It works like this. I can't even. It's called I Can't Even. And the idea is that you take out the even part and the odd part of your function. You're trying to integrate over some symmetric integral. Now, symmetric interval. Now, you know that if f were an odd function, you would say it's 0. Yay. because the integral of an odd function is 0 over a symmetric interval. If it were an even function, then you would have to go and integrate it. Boo. What you can do is split out that function into an even part and an odd part. Language is hard. You're going to write this as even part plus odd part. And then, great news, you only have to integrate the even part of your function, because that horrible odd part just integrates to 0. So this is fantastic news. You only have to integrate the even part. But wait, you're saying at home, how do I find the even part and the odd part of my function? Well, there's a handy formula that for any function, you can write f of x. Is this grating, doing the kind of TikTok presenter voice to people at home, like you're a kind of primary school audience? Like, hey kids, you can just write f of x plus f of minus x. Feels grating to me. Probably shouldn't interrupt my great TikTok reel here. F of x plus f of minus x divided by 2 plus, and here's the odd part, f of x minus f of minus x over 2. So this is great. This means that in practice, all you need to do is integrate this thing, f of x plus f of minus x over 2 with respect to x. Hooray! Yeah, this should be several TikTok videos, right? Join me in part 2 to find out how you find e of x and o of x. It should really be called I can't odd, because I can even, I have to. It's the odd part that I can't and don't have to. You design this so that the function contains a nice even part and a horrible odd part. Still, I'm sort of being a bit snarky, but I still think it is quite a good contribution to find the in this case even part of this, where you know that k of x, k of minus x is equal to 1. I think that's nice. I think that's good. It simplifies really nicely. The even part is just 1. So now I do want to think about functions where the even part is the number 1. Can you multiply that statement by 2 and get, multiply which statement by 2? If I've done it correctly, then it should read f of x equals f of x. This one. The reason this thing is true is just because I've added something. Oh, the integral. Multiply the integral by 2. Well, it's still integrated. I guess I'm taking one copy of f of x, and I'm taking a substitution to get the integral of f of minus x, which is going to be kind of the same by integration by substitution, because the limits don't change. They get flipped, but then the minus sign from integration by substitution flips them back again. So you can integrate f of x or f of minus x. So I guess you can multiply by 2. You don't get f of x equal to f of minus x, you get the integrals of those things equal to each other. And the integrals are equal because of integration by substitution. I don't know if this qualifies as a cool fact, but this is true for all functions, not just even functions, just anything. Ooh, inverses rather than odd and even functions. I feel like I have seen a lot of things in the space of cancelling out the denominator of a fraction. Wait, have I got one in here somewhere? We did a horrible step question once. I think I've still got it. Oh no, I can't say it. We did a step question once. It was not that one. Okay, never mind. Integration. And switch. So do tell me about other integrals you want to do. Oh, that sort of thing. Yeah. If you translate this fact, it looks more mysterious. Sorry, that's me being snarky again. But same idea. And the third thing someone showed me, which I thought was really good, is this Maths question, where you're supposed to be finding this area And the idea is parametric equations, created by Maths. Shout out to mathsmaths.com. You're trying to find this area, and their question was really good. It was, why do we use limits? And the way the question is set up, you just write down theta 1 and theta 2. Why do we use limits of p and q and not limits on the kind of x limits of integration? Yeah, I heard they passed away. Sorry about that. Tribute, I guess. It's a good question. This is a nice question. It's a good curve. The interesting question is, why do you integrate from kind of theta, the value of theta here, all the way around to the value of theta here when you find the area? Shouldn't you do something like integrating between the x limits? This pen's a bit too thick. Integrating between the x limits and then doing some sort of subtraction, or carefully integrating until you get this far and then doing a separate integral over here. So sort of middle integral and then something clever around here with some subtraction. And that's kind of what we advised the student during the call, when we had a call with some students. But I think we missed a trick. I think we should be talking about how you can just put in the theta limits. The plan for this question, I think, is that we're integrating y dx, but we're doing that by doing y dx per d theta. And the theta limits are just the values of theta at p and q, which I think is cool because it loops back around again. So that's good. It loops back around again, but we don't worry about that. So I tried to make a visualizer for this, which I showed you by mistake a second ago. So here's the curve in black, with the limits being pi over 3 over here on the left and 5 pi over 3 over there on the right. I've got this slider so I can show it being drawn from left over to right. And it starts by going left a bit and then coming round, and it goes past this kind of maximum and back in again. And we would like to find the area inside that curve. So I made a visualization thing to try and show what's happening when you integrate with respect to t, the parameter here. Is it theta in the question? Yeah, I think it's theta in here, but for Desmos I've used t. When you do that integration with respect to t, you're splitting up the area into these different boxes, which have got different widths. The kind of normal way to do integration would be to integrate this with respect to x. It's the first thing you learn. But if you do it with respect to t, you need to allow for the fact that as you change t, the boxes are different widths, because every time you change t, the point moves horizontally quite a lot. I mean, you saw it as it was going, right? It moves faster in the middle, so these boxes are wider. Yeah, if you have t changing like a clock, like it is in here, you've got these boxes that are wider in the middle. Yeah, so this is, I guess, I think I'm doing a sort of normal integration, but after a substitution. So substituting for this parameter t. We've just got sort of wide boxes and narrow boxes. But then the thing I want to really zoom in on is what's going on as it comes back again. And for this, I think I need more boxes. So let's increase the count like that of how many boxes we've got. And I just want to animate the last bit to show what's happening as it comes in. You maybe saw it there as I reversed it. As it comes in, it kind of turns around and comes back again. So there's a little bit here where, as you're integrating, dx per d theta is actually negative. So although these boxes that it's drawn on the way back kind of look the same visually, for those ones, dx per d theta is negative. So that bit of area is being subtracted as we come past it the second time. So it's kind of naturally subtracting the area underneath the curve for us. If you just keep going with respect to t, or theta, or whatever it's called, if you just keep going, Don't stop here. Definitely don't stop up here somewhere when you get scared that it's not single valued anymore. Don't stop up there. Definitely keep going. And then on the way back, it's got this kind of area that's negative and just cancelling out the thing underneath. If I rescaled the x-axis, it would be, yeah, it'd be evenly spaced if I did the rescaling. And then there'd be something interesting about how it's folded back over to subtract some of the area underneath. That's also happening over here. And I think we missed a trick by not pointing this out to the student, because this always happens. That if you have a parametric curve, let's go back to Miro quickly. This always works. If you have a parametric curve, so some weird blob like, can I make it look more wobbly? Yeah, let's go, let's be E. Popular with Gen Z, who I understand have E as their favourite letter. There you are. There's this brilliant fact that however you parameterize the curve, if you integrate y dx around C, people normally just write C or something here, or put a circle on here to say that you're integrating around, if you've seen a cool integral sign like that. But whatever, you integrate around the curve, all the way around, then you get the area. Or maybe you get minus the area. Some people believe strongly that areas should be positive, whatever. Look, the magnitude of this thing is the area. That's got a name. It's called Green's theorem, or it's one example of Green's theorem. Green's theorem actually tells you how to do lots of integrals like this, where you integrate all the way around a closed curve. And it doesn't matter that the curve loops backwards and forwards on top of itself. This always works. So I guess I knew Green's theorem, but I never really probably kind of appreciated how weird it is that that just works, that it keeps subtracting the bits of area as you go round. I've tried to set this up so that I could put in a different curve to show you the kind of doubling up, but I think it's just going to show you lots of areas on top of each other, right? And it'll be a little bit unclear. What I'd really like is to tweak this Desmos code so that the bit where it's coming back, it draws red rectangles and makes a cool kind of purple cancellation colour. And I'd also like it if the function went below the curve, it drew it in red so that it would be a negative bit of area. This is kind of cool thing that I try to imagine, and it's not a visualization of this quite yet, but this is kind of like a kind of curtain or a sheet of material that's actually a different colour on the other side, so that as that integral curves, as the kind of thing curves round, you're seeing the back of the material, and then, unlike any material I've ever met, front-facing and back-facing material cancel out to give the 0. Those things count as different things. And that would be quite a nice visualization, I think, because you could have a curve going down under the axis, and as it goes under the axis, it would look like a kind of 3D thing turning over and coming back again. So I should probably work on that. But I think what I'm actually going to do is, yeah, edit it. Ooh, that sounds too clever for me. Oh, yeah. Yeah, so for this curve, I could probably do it separately, to do these 3 separate parts, to say I want to rev it over here. The tricky thing is to do it in general. I've set it up to accept any functions f and g, and Desmos is maybe not the best tool for this, but it's got the animation built in, the sliders, including this first bit where it's going, if I play it forwards in time, it's going left, so this is negative, this kind of should be red to start off with, and then a bit of blue, cancels it out. We've got this kind of thing curving around and cancelling itself out. But I normally don't do this, but I'm going to call it a day at 3 o'clock. Even though... Can I shade polygons with different colours? Okay, homework. Here's the Desmos. Here's a copy of the Desmos. I don't know how to do any of this shading with different colours, and I don't know how to make this, generalize into this kind of if the curve is moving left, if the rectangle's drawn the other way, it should be able to detect it from like the corners of the rectangle. You could do some if statements or something in a programming language. You do some if statements to say, if you're about to draw a rectangle that's the wrong way around, change colour. If you're about to draw a rectangle that's that way around, change colour. You can define colour in the back of the rectangle, I think. But I don't know how to do it in Desmos. So, good luck everyone. Or did I give you a Desmos for an out-of-date version of this? I did, but not significantly different. Okay, cool. I'm calling it there. Have a good Sunday afternoon, everybody. I think I'm back next week. Do a nice short live stream. That's what we sometimes do. I'm back next week, and I might see some of you on Matt Livestream or other things like Opox. What was a short live stream? I'm going to go off and have a bit more Sunday. I normally do 2 hours Neutrino. I normally do 2, but I really want to go and watch the British Grand Prix. I'm sorry. Take care, everyone. I'll see you next week. Don't forget to have a tea break or something in my absence. Right, okay. Understandable. How dare I put my hobbies and interests ahead of maths. Maybe I'll do some maths at the same time. I can have a laptop doing the same. Yeah, okay, right, bye.